Welcome to lecture 10 of MCS 507. So in this lecture, we are going to see how Julia interacts with other code. So there is a large, extensive ecosystem, many packages that are available in Julia. But it's important to realize that Python can also, Julia can also interact with existing code. So this is our fourth week of the course, and we are switching into Julia, another language. Can we throw away everything we know or everything we tried to study from Python? No, far from it. We can call Python code. We can also call external programs. That will be an opportunity to indicate how to work with files. And then Julia is also quite efficient in calling C code. So on the whiteboard behind me, I've tried to indicate the plan of this lecture. So we can use all the Python modules that are available in the Python interpreter via PyCall. We can run external executables, and then we can also call C shared object files or C compiled code directly with ccall. So compared to Python, calling C code is actually easier from Julia. Okay, so there is a very large community of scientists and software developers using Python. Please visit the web to check out this very large ecosystem of packages, also quite wide in the diversity of fields that it covers, and there is always the miscellaneous at the very end. So there is also the packages website that provides a point for the software available. So that is an idea that comes from Python, having package managers that help you installing software is actually critical. So installing software can be a hassle. So a good package manager actually takes care of those troubles. So if you are curious, if you have if you're curious on your software, and if you land on a machine where you don't know what is installed, you can check the path and see where, in which folders, Julia has placed the packages that have been downloaded. Again, there is extensive documentation, so it is easy to get overwhelmed. What I will try to do in this lecture is kind of a very quick how-to, give some directions in how you can get started with Julia and linking in existing software packages. Okay, so we worked 3 weeks with Python. So we started in the second week with NumPy. So should we forget everything what we have now done with NumPy? Far from it. So here is pycall. So we can import the numpy module with pyimport, and then call the functions exported by the numpy module. Again, so this requires that pycall is installed. So this doesn't come with the standard library. So the first time that you do using pycall, you will have to answer yes to continue and be a little bit patient depending on your network. It's also quite possible that you have multiple Python interpreters on your computer. And you will know this if you have already used NumPy in a Python interpreter that is different from the one that Julia is using, then this will not work. Although there is documentation to set the environment, it is possible to use a different Python interpreter, different than the default one that Julia uses. I should point out here that there is also the numpy.jl, so the N and the P are then capitalized. So there is a wrapper package, Julia package proper, that incorporates most of the NumPy functionality. So there is also a simpy.jl, again the S and the P are capitalized then, and there is a scipy.gl. So this implies that the widely used functionality of NumPy, SymPy, SciPy is actually hereby almost automatically also transferred to the Julia user. So the packages that we have seen in the second week of the course are still available. So that's the main point of this slide here. It shouldn't be necessarily be done by pycall, but I'm introducing pycall to indicate how we can use our own modules. Here is our own module, and I executed this at the terminal window or in a PowerShell on Windows. So thanks to the PowerShell, many of the basic commands that you can find also on Linux and on Mac, you can actually now also execute. So we have our very basic simple module, which is a hello world. So it allows me to emphasize a little bit the way Python modules work. So we have collections of functions. We can have a main program here. So this is the hello world encapsulated in a function. But we can also import the say hello function. So if we execute at the command prompt this file, then the main program will run. If we import this as into a Python session or also in a Julia section, as we will do immediately, then you can say I want to call the function say hello. In a very similar manner as on the previous slide, I called the cosine function from the NumPy module. Okay, so there is some magic on this slide. So one has to extend the Python path. So it's not automatic if you run Julia in the current folder and your Python module is there. It's not automatic that the pyimport will also find it. So there is the path that was in the system module. So you can also, so the pyimport that we're going to use later in the session here at the bottom of the folder can also be used to insert to the path the current folder. And that can be done with one simple command. That's to push first with the exclamation point. So this is going to change the object it applies to. So you see the py import. We import from the sys module the path. This is a list. It gets as a py object converted to a vector, because push first works on an array Julia type, and we insert the current directory. So the magic here is this notation at. So you can extend, you can change this command where here you provide any folder name. So if you have all your modules stored in a particular folder, you can use this. So I'm running this in an interactive Julia session, but this will also be quite important if you run this in a Jupyter notebook. Okay, so that's mainly it. So we can import then the Hello Python module, and then call from the Hello Python module any function that is exported by the module. So in this case, it is say hello. So with the ... here, I left off the specific information that is specific for my installation. That will depend on where you have installed it. If something is not working right, you will receive an error message. Most likely because Python might not be correctly installed, or PyCall might not be working correctly. So there are two ways how to run functions, either via the first hello, the py import, importing the module and then calling the particular function, or you can also do everything in one command. That is the last command here on the session. Okay, so this is the first topic that I wanted to present in this lecture, how to call Python code. All right, so the second way to call external code is via calling executables, something that we did in the last week. Remember the MP-solve. We are going to do something very similar here. So for that, we need to store files. So write two files. Here we store a 32-bit approximation of pi. So we first make the string representation of pi. So pi, by the way, perhaps Julia is a numerical program, but pi is a constant, is a letter, and that we can approximate up to any precision here. So the big float is very well nicely integrated into Julia. So this is another illustration of that feature. So I have my 32 decimal places approximation for pi. I make a file. Syntax is very similar to Python here. I write that string to file, and then I close, and then I make the string representation of pi vanish because I want to read it. So I open the file again, but now for reading. Then I read a line. I have to make sure that the precision is set fine, and then I parse the string into a big float. So 110 here refers to the number of bits, which is roughly corresponding to 32 decimal places. Okay, I demonstrated this in an interactive terminal session. It might be interesting in the cloud where your files are going to end up with. You may, on your own computer, provide the absolute path name in the file name. So here I have openstore32py.txt. On my Jupyter notebook, when I launch the Jupyter notebook in the current folder, it will also, the files will appear in the current folder, which is fine in a local installation, in a local run. Okay, how do we call external programs? Well, I indicated it, it is run, so we should point this way, run. So what I do here is I make there is so this is most likely the program that I store here in say hello is a bash script, so that might not work anywhere else other than Unix or Unix-like machines. So I run the say hello. So say hello is oh, I'm sorry. So I'm using the syntax that can be understood by a run as defined by Julia. So I'm defining in say hello an executable program. So run will will run a process. So here I defined it. The backticks are important. So here you can see the left quotes and the right quotes. So the left quotes are used to echo the hello world. They show up when the process is executed. So the right quotes or the backticks, so the left ticks, backticks, have to be used in the arguments here. Okay, let's start. So we can. So this is particular for Linux now, although also the PowerShell has the ls command. So we can check in the current folder how many Julia programs are there. So we list all the files with the extension .jl in the current folder. When we did the wrapping of the MP solve, we worked with the less than and the larger than symbols for the redirection. Here we can't really do this, so we have to work with the pipeline. And the pipeline is illustrated here. If you have been using Unix a lot, then it's quite familiar to you. So what does the pipe do? It pipes the output of one program, the ls here, the directory listing, to the input of another program, the grep. The same happens here, but we have to provide the pipeline. So, and this is here a nested pipeline. So I will, so if you run the pipe ls, then the pipe symbol grep, then you will see it on screen. But here I will make another file. So this is so the code here that is listed is the content of a Julia program where we run the pipeline. So it's running two pipes. So the ls, the output of ls is piped to the input of the grep, and then the output of the grep is piped to the listing file. So the standard output is in this way redirected. And then what the Julia program does, it opens that listing file for reading, and then it reads all the lines. So the read lines is also familiar from working with Python. And again, if you're coming from Python, you will forget, as I usually do, you will forget this end. All right, we're now ready to call an external root finder. I will use not mpsolve. I will use this as an exercise. So in some sense, the exercises that you would have been doing for last week are still useful here. But the principle is the same. So wrapping a program from an executable is a very powerful and useful mechanism. So we have seen this with Python, and I think it's very useful. So it's something that you can do if, for example, you have a black box solver that you like to use and that you like to import in the Julia environment, then this is a very good way of working. So as long as your program is working on your computer, it doesn't matter in which language it is written. You prepare the input, call the program, run the program, and the output file is then redirected to the output. So this works. So I will simulate the wrapping here. I will actually use as root finder the eigenvalues of the linear algebra module. So we can get the eigenvalues from the linear algebra module. If we write the companion matrix to the polynomial, so we store the coefficients of the polynomial has to be monic. And it's important here, I used the Julia convention, although I think it's very awkward. And I think I may have done, so there is a mistake here, so it's so awkward that I made a mistake. So I have to fix this still. So I'm not used to having polynomials starting with C1. So actually we have Cn coefficients here. So this had to be Cn to the very end. And we make the polynomial monic. So which means that yeah, so there's still something wrong here. So we have n minus 1 coefficients in a polynomial of degree n minus 1. So so if there was a coefficient, so in general, a polynomial of degree n has n minus 1 coefficients. So if you want your matrix to have dimension n, then I think by now you get the idea. Okay, the program has it correct. Don't worry. So I will be using the extension to. So this is a programmer's perspective now. I'm taking the opportunity of this wrapping exercise to illustrate some features of Julia. So Julia allows to define polynomials to wrap in a very, very short way. So we can wrap polynomials over any ring. Polynomials here naturally, dense polynomials may be represented by their coefficient vector. So I can make that object immediately callable by defining the bracket operator. We've seen in Python how to define classes and how to define callable objects by the overriding by the call method. Here we are doing something very similar. So on a polynomial, we can apply the bracket operator. So if we have a polynomial object, we will be able to write p and then between round brackets a number to evaluate that polynomial. By the way, so if you have to work with polynomials in a quicker way, there is the eval poly that is exported in Julia. So the main point here is for me to illustrate the definition of a polynomial of any ring. So the extendable typing system is very good here. So I don't have to restrict myself to any type when I think about polynomials. There might be integers, there might be big floats, there might be 64-bit floats. And by the way, this is Horner's method, another way to show the array processing. So the running through an array, starting at the highest coefficient and peeling off down. Then we have the setting up of the eigenvalues of the companion matrix. So here I'm using the eigen method, but one could perhaps written this a little bit shorter to call immediately the eigenvalues. The eigenvalues is actually a function exported by the linear algebra module as well. I should not say anything much about the code here, which is kind of incomprehensible if you don't see the definition of the companion matrix in front of you. Then there is the testing. What I'm, by the way, I should have told this earlier, what I'm doing now is to set up the root finder that will be called from Julia program. So this is a mock interface. I have one Julia program calling another Julia program, but then via its Python, via its Julia system. So this is something that you do not want to do, but it's good to illustrate the point. Testing is very important. I will test this for a random polynomial, and here you see the evaluation. So I evaluate the polynomial. So I create a polynomial from a sequence of random coefficients. They will all have positive values. So in some sense, I will certainly have complex conjugate roots. Perhaps I could have taken an even power, an odd power. Then you know that there will be also one real root there. The syntax is very nice to evaluate a polynomial. So we can work with the polynomial p as if it were any other function. So the distinction a little bit between the data and the functions is quite nice. So one can treat the object polynomial as it is a data structure, but one can also treat it as a function. This is very nice. Okay, so we test the residuals. So this is a test. And then if we want to, perhaps in the Python philosophy of defining classes, the next thing would have been the string representation. But here we start with the reading later. So this is the input and the output. So the output was just a representation of the coefficient vector. For the reading, we parse. So I will parse to complex 64-bit float representations. So that will limit in this interface the type of polynomials I can handle. But I will go to a numerical eigenvalue computation. So we build up the list, and from the list we make the polynomial object. So the constructor to a polynomial is flexible enough to take a list as coefficients. So the vector, so perhaps I should scroll back now. So what this does, it takes the vector. So when we make a polynomial object, what will happen is that we will make a vector representation. So the constructor can take anything that can be converted into this vector object. So what we do in the read, I start with a list. So this way of working is quite similar to how you would work in Python. So you would append numbers one at a time in a list. And this is quite convenient and quite natural when it concerns the input. But then with the processing, it is automatically converted into an array, which is then very convenient for efficient evaluation. So in a couple of statements, we do a lot of work that in a traditional compiled language would have taken a lot more time. So defining a linked list in a data structures course, if you ever have taken one, took quite some time if you have to implement this in C. And then one needs to convert the linked list also to an array for efficient evaluation. This is done here straightforwardly. Then there is the interactive test, and that defines the setup. So we have the reading of the polynomial, where we read line after line of the input given certain degree. Either if the degree is 0, then actually we prompt for the degree. And then we read the coefficients. So the output, I said that there was no string representation, while we are using the standard representation on how any coefficient vector is displayed here. Okay, half of the work is done. We have our interactive test. So this is the external root finder that will be called. So this is the poly roots. And everything is here set up to work in command line interface. Okay, so then the other program that will call that root finder will first have to make an input file. So in the input file, we will write the coefficients line by line. So that is done here. So the input will here also really make the input, starting from the dimension, which is the number of coefficients. And it will print the coefficients with the standard notation, scientific formation for the numbers. Then we have the parsing of the output. So the output is again a sequence of floating point numbers. So in a way, we can test the input and the output in a very nice way. So we have input that are coefficients, output that are coefficients. So this can be done most likely much more efficiently via the built-in. But this way of working has the advantage that it will extend quite naturally to different types and to different formats. So it also shows the explicit parsing. So we essentially expect the output that can be represented, that can represent a complex number, line by line. Then there is the main program. So the interface to call an external root finder consists of three functions. So the making of the input, the calling of the external code, which is here essentially the run. So the third function is the main. And then we have the processing of the output, the retrieval of the output. So it's very similar to what we did last week, but I find this way of working a very useful way of integrating and starting to integrate external programs, making your programs also more useful to others. Starting from a prototype that you often only want to release in an executable format. Okay, so I have about 15 minutes left for C. So in the last lecture, to check the performance of Julia, I was going from C, Python, Julia. Now we have Julia, Python, C. Python Python can call C programs, but we have to define and compile an extension module. So we have done this, but it was quite involved. Even if you use the Python setup, there is a lot of boilerplate code that needs to be defined. And again, finding the right compilers, the right libraries might not be that straightforward here. The standard C library is immediately available to the Julia user. This is very nice. If you have your own C code, make sure that you compile it with the option shared objects, and the position independent code, the fpic options. So we can illustrate how we can call the random number generators from the standard library. Also, we can call the clock. So these commands work directly, and they do not take any input arguments. So the last tuple here is empty. So by default, if we do not provide the library, so libc can be omitted, then actually the cc call assumes that you have the standard C library. So the Julia programmer has actually immediately the standard C library at their availability. So this at their disposal. So the C library is immediately there. Here we can look at the environment. This could be very useful if you want to write Julia programs that have to interact with the operating system, and you want to check which type of shell that is being used. So here ran this on the Bourne shell. I'm also wanting to illustrate here that what is returned here is a C string. So I should probably have been a little bit more careful in explaining the arguments of ccall. The first argument is the name is a tuple with the name of the function and then the name of the library. Then the second argument of ccall is the return type. Here it is a C string. Then the next argument is then the input type. And then come the values. From the environment, I want to know which shell is used. So shell is the input string to the get_env command. And I can take what is returned by ccall. So it is a pointer to a string, and it's not safe to work with pointers because they may disappear or be reassigned or something bad may happen to them. But I can convert them anyway here. And in a readable string. So that's the output. If you would type in env at the Bourne shell, you would actually also see that information somewhere in the shell variable. So you can actually query the variables, the values of the variables, the environment variables that are being set. Here is a more elaborate version. So one can get the host name. So get host name is also a function of the C library, but we can get that host name as a proper Julia string. So this wraps everything. So I initialize so I make actually the host name now. So the return type, so the get host name, actually can also work with a string as on input. So I can provide here the location of a string of characters, which is unsigned 8-bit integers. Yeah, so the precise syntax. So you can also see here, I should have read the documentation string first, how the memory allocation can be done from within the Julia session. We did something very similar with the wrapping of the revert string in Python. So we had a string that was made in a Python session, and we passed a reference to the C code. Something similar is happening here. So we have a host name string, space allocated for here, and we pass that space to the C code. We pass the pointer to it. Okay, so that was not so useful, perhaps. What is next might be more useful for showing a more elaborate wrap. So C, the standard library, also exports qsort. The function qsort is extremely useful. With this wrapping, I like to show also a little bit how the C mentality, how C can be extremely flexible as well by wiping out type information using the void. So the qsort will work on anything that can be compared, provided that you tell C how to compare. So in C you can also pass functions. So what we will do in the next wrapping, we will wrap a Julia function and pass the Julia function to the C code. So what we have further, we have to provide, so we have to provide a pointer to the first element in the sequence. We have to tell C how many elements that there are, and we have to tell the size of every element. So size underscore T is the C type for using for positive size information, positive integers, size types. But for the rest, you see the voids coming in here. C supports strong typing, but as if you really want to be ignoring all that, everything can be can be voided. So it is powerful, but also most likely unsafe behavior. Now, here how it is. So we define what is called a callback function. In a way, this is also a very good way of building interfaces. If you build your own library, it's often extremely good to provide a callback function. So that is a function that often allows to provide at least some information to the user of your program. That the user of your program has a way of tracking, especially in long computation, what is actually really going on. In a more powerful way of providing interfaces, you can give the user way more control. Julia and C are friends. You can say here we can have C code, compiled C code, execute Julia code. How does this happen? I have the comparison, and I could have coded this up in a very long if else, but here I have the conditional statements. So if A is less than B, I will return -1. So I have to respect the compare syntax. So I did not give the documentation of qsort. So qsort expects that the comparison function gives -1 if the first element is less, +1 if it is larger, or 0. So I have to respect that convention, of course. Okay, to make it available to see, I use this macro, the crawl, the a crawl, and then this will be a C function that will take on input two references. And here I have to provide the references. So there are references to doubles. And I was probably a little bit too enthusiastic that I said that qsort could compare almost everything. It might very well be that this is in the end limited to comparing doubles. So this is where the void is a little bit delicate. But it might be interesting to actually try this. If you have arrays of composite data structures, can you still sort them? Most likely you can. So then your array would be an array of pointers to whatever composite data structure it is. Okay, let's try this. We are happy if we can sort a sequence of doubles. So we will generate a random sequence of 16 positive doubles. And then we call qsort. Qsort is part of the C standard library. So I admit the name of the library. It returns a void, so the return type is a C void. It takes on input a pointer to a double, size type, two size types actually, and then the last input type is also a pointer to a C void. So a function here is also just a pointer to something that can be of any type. So you see the types of the four input arguments, and then followed by the actual arguments. And the actual arguments, they are Julia objects. I have a Julia array, the length of the Julia array, the size of the array, the size of any type. So I can make this also quite generic. And then my compare function that is passed to the C code. Okay, what I just said is here once more explained. So it looks more technical, but if your library is again available, and here I was doing this with the C standard library, um, to be a little bit more general, and I've tried this out, if you define the location of your shared object, and the shared object can be a DLL file in Windows, can be an SO file on Linux, can be a Mac OS on a dilib file on Mac. So I've tried this out for all three operating systems, and this is a very flexible mechanism as long as it's properly defined in the C code. Okay, so the summary is that Julia plays very well with others. So we can call the efficient C code. So the C code is over here. We can provide anything that is available in Python. So the Python and the C world are actually closer to each other than what is seen here. Or we can also immediately run external executables. So these are the three types of interfaces that we can make. So thank you for your attention. So in the next lecture, I will try to indicate how one can now do scientific computation, give some more illustration on how what Julia has to offer, how one can do scientific computation.